Hello everyone! So welcome for today's video presentation about the open channel in fluid mechanics, specifically the trapezoidal channel. So I am Norhamian Balabagan. In this session, we're going to solve a problems regarding trapezoidal channel that are crucial in hydraulic engineering and water management.
But before that, let's make a brief introduction about trapezoidal channel. So, unlike rectangular, circular, and triangular channel, the trapezoidal channel offers a balanced combination of stability, efficiency, and versatility in fluid flow. They are commonly found in rivers, canals, and irrigation systems worldwide. Next, in solving problems, we have here the key concepts that involve, such as understanding the geometry, characteristics of flow, including the flow rate using the continuity equation, and also the velocity using the Manning's equation. We also have here the hydraulic calculations such as the hydraulic radius and also the critical depth. So now let's try to solve a sample problem. Determine the uniform flow through a trapezoidal concrete lined canal having side slope of 3h to 4b and bottom width of 2 meters if the depth of flow is 2 meters. The channel is laid on a slope of 3 meters per 2 kilometer. Use n is equal to 0.013. On this problem, we need to determine the flow rate through a trapezoidal concrete lined canal with specific dimensions and conditions. So given the data, we have here the figure. Imagine that this is our trapezoidal concrete lined canal. So we have here the base width, which is 2 meters, and also the depth of flow y, which is 2 meters also. This is the vertical distance from the bottom to the water surface. We also have the side slope z, the distance per unit vertical rise of the side slopes given as 3h to 4v. This means for every 4 units of vertical rise, there is a 3-unit horizontal distance. So side slope ratio z is equal to 3/4. We also have the channel slope s. The slope of the channel bed given is 3 meters per kilometer. Also, the Manning's roughness coefficient n, a coefficient that accounts for the roughness of the channel surface, given as 0.013. So now, we're going to solve the flow rate using the continuity equation, where the flow rate is the product of the flow area and the velocity. So, using this equation, we can solve for our flow rate, where the Q is the product of the flow area and the velocity. But first, we need to know what is our area. So, the flow area is the cross-section area of water flowing through the channel. For a trapezoidal channel, we have our area A is equal to by plus zy squared, where b is the base width, y is the depth of flow, z is the side slope ratio. Plugging in the values, we have here now A is equal to 2 multiplied by 2 plus 3/4 multiplied by 2 squared. And in solving, it resulted to 7 squared meters. So now, we have the value of our area. The next is the velocity. Using Manning's equation, we can find our velocity. This Manning's equation relates the velocity of flow to the channel's roughness, hydraulic radius, and slope. So we have here the formula. V is equal to 1/n r to the power of 2/3 and s to the power of 1/2. So where our v is the velocity of flow, n is the Manning's roughness coefficient, r is the hydraulic radius, and s is the channel slope. But first, we need to find the value of our hydraulic radius since it is not a given. So, in finding the hydraulic radius, we have here the equation R is equal to the area divided by the perimeter. So, the ratio of the flow area to the width perimeter. So, given the area, we also need to find what is our perimeter first. So, in solving the perimeters, we're going to use the equation P is equal to B plus 2y square root of 1 plus z squared, where our b is the base width, y is the depth of flow, and z is the side slope ratio. Plugging in the values, we have here now p is equal to 2 plus 2 multiplied by 2 and the square root of 1 plus 3/4 squared. In solving this, we will arrive into the answer 7 meters. So our P now is equal to 7. So since we have now the value of P, we can now solve for our hydraulic radius, where our R is equal to A over P. Plugging in the values, we have here now 7 divided by 7. So we will arrive into the answer 1 meter. Since we also now have the value of r, we can finally solve for our velocity using the Manning's equation. V is equal to 1 over n r to the power of 2/3 and s to the power of 1/2. So plugging in the values, we have here now V is equal to 1 over 0.013, and this is a given, multiplying into 1 by our radius to the power of 2/3, and also our slope, which is 0.0015 to the power of 1/2. So from the given slope 3, we converted it into dimensionless. Since the slope is said to be 3 meters per 2 kilometers, we need to divide this into 2,000. And we have now 0.0015. That's why we have now the value of our S, which is 0.0015. Now, we need to compute each part. 1 to the power of 2/3 is equal to 1, since any number to the power of anything is still the number itself if the number is 1. Then, 0.0015 to the power of 1/2 is equal to 0.0387. Therefore, we have now V is equal to 1 over 0.013 multiplied by the value of our R, which is 1, and the value of our S, which is 0.0387. In solving this, we have now the value of our V, which is 2.98 meter per second. So now, we have the value of our velocity, and we can finally solve for our flow rate, where our Q is equal to the product of our area and velocity. So plugging in the values, we have here the area 7 multiplied by the value of our velocity, which is 2.98 meter per second. In solving this, we have now Q is equal to 20.86 cubic meter per second. So, the flow rate for the given trapezoidal channel is 20.86 cubic meter per second. By understanding each step and the corresponding formulas, we can solve similar problems for any trapezoidal channel flow scenario.